No eating in class, Jay. Just kidding.
I also have yogurt pretzels.
Oh, that's no fair. I want yogurt pretzels. I have sourdough pancakes. Took 12 hours to make. So good. Most of that 12 hours is spent sleeping, of course, but so as we talked about yesterday, the tangent graph, we use most, if not all, of the same principles that we used for sine, cosine, and that we would use when graphing sine and cosine to be able to build secant and cosecant. The major difference is in the period. So our amplitude is still that absolute value of the coefficient of the function. So in this case, the absolute value of the positive 3 is just 3. The amplitude doesn't matter as much, and we'll talk a little bit about why. We almost ignore amplitude for tangent, and frankly, for our purposes, you can pretty much completely ignore it. I will show you where it comes up, but it's more subtle than it is for sine and cosine. Our fundamental period, our basic period for tangent is only pi. So when we find the period, we take the normal period and divide by our compression factor, just like we did for sine and cosine. The difference is our normal period for tangent is only pi. So do be careful about that. If you're wondering where's that to, it's because we're dealing with tangent here. Our phase shift, though, is done the same way. That function is being shifted by pi over 8, but then that shift of pi over 8 is being compressed by a factor of pi over 4. So our resulting phase shift is just that 1/2. As we talked about, you could also just factor that pi over 4 out if you prefer and get x minus 1/2 to write it in that form if you want. Either way, you're still dividing that pi over 4 out of the pi over 8, either doing it outside or doing it in the expression itself, whichever way you'd prefer. And our lift, of course, is the same. It's just that constant on the end, going to push this whole thing up by 1. So our equilibrium line, our center line, is going to be at 1. So I'll put that there. I'm going to go ahead and put in that amplitude very lightly. As I said, it's not going to matter as much, but I do want to show you where it is. That is not lightly. That's better. So, because for sine and cosine, this line is where our maxes and mins are. But as you recall, our graph for tangent doesn't have maxes and mins. It's just those big sweeps. So it's not going to give us the kind of constraints that it does for sine and cosine. Remember those asymptotes were at pi over 2 and negative pi over 2, because that's where the tangent function became undefined. But it does still have a representation, and we'll talk about it when we get to putting the actual graph in. So I do kind of want them there just so we can talk about it. Now, normally, tangent has that sweep centered at the origin. That sweep is going to move up because of the lift to that y value of 2. No, sorry, that y value of 1. That's why we label things. So 4, that's a negative 2. So it's going to shift up to that y value of 1. But that phase shift of 1/2 is also going to move the function that way by 1/2. So it's going to go, let's say over here to 1/2. So that's this central point moving up and over because of the up and the over in our transformations. Now these asymptotes, normally these asymptotes go a total distance of pi, our period. Notice it is half of that pi in one direction and half of that pi in the other direction. So for our tangent up here, that period is 4 now. So it's going to do that same thing. It's going to be 4 in length, but I don't want to go from this point out 4 to put my asymptote. Because again, remember this middle point here is halfway between those asymptotes. So I essentially want to split that 4 in half and go out, see, if that's a 1, go out 1, 2 in both directions. So we're going to have an asymptote there at 2.5 and an asymptote there at negative 1.5. So I'm going to make those darker, make sure we can see them. So that's probably the biggest error that happens when people graph tangent is they go from that center point, they go the period distance in both directions. That makes the distance between the asymptotes, in this case, it would have been 8 instead of 4. So it ends up doubling our period. Now, if we wanted to count from this asymptote and say, hey, where's the next asymptote? Well, that next asymptote, the distance from asymptote to asymptote is still 4. The distance between negative 1/2 and positive 2.5 is 4. So this next one is going to be at 6.5. And same with this center point. If we want to go to the next center point, that's going to be at 4.5. So it's still the same. The distance from any occurrence to the repeat of that occurrence is our period of 4. Just be careful when you're counting from where we kind of think of tangent as starting in the middle. We don't count out the full period like we do for sine and cosine, because that kind of anchor point is not at the beginning of a period, it's in the middle of a period. Does that make sense? You guys good with that? That is by far the most common error people make. I'm going to assume by the awkward silence that you're happy. I don't usually think awkward silence implies happiness, but well, Felix is happy. That's good. And Dominic's at least smiling. Okay. So hopefully that seems reasonable. So be careful about that. Now, normally Again, with sine and cosine, at a quarter of the period, we reach a max, and 3/4 of the period, we reach a min. That doesn't happen. But what does happen is at that quarter point, it's going to occur at pi over 4 and negative pi over 4. We do know what the tangent of pi over 4 is. The tangent of pi over 4 is 1. So at pi over 4 and negative pi over 4, at the quarter points, just like sine and cosine, we still at those quarter points get 1 and negative 1. That 1 and negative 1 just aren't our max and min anymore. So we can do actually the same thing with tangent. If we want to consider that amplitude, we could go halfway between those two. Halfway between 1.5 and 2.5 is what? Well, 1.5. So at a quarter of the way through that sweep, instead of being 1 above the center line, we're going to be 3 above the center line. So it gives us a kind of a target of where we should expect that sweep to be. That's just -1, yeah. So we don't really have to draw those in, but it can be nice to give us a sense of how stretched out that 3 has made our tangent graph. And then we can just put that sweep in there. Trying to, oops. I don't know why I did that. Sorry. Put that sweep in there, having it do its little inflect at our center point. And it's going to go up and be asymptotic to that 2.5 and asymptotic down here at the 1.5. And repeat. You can make your dots bigger if you miss. And boom, we got a graph of tangent. So really, as I said, the big thing about tangent is being careful of that period. Really, all the tools are exactly the same as the tools we've been working with, except that the period is only pi, and we really think of the graph as being centralized in that period as opposed to being at the beginning of that period. So those two things take some adjusting to. But other than that, the tools are very, very similar. Questions about graphing tangent before we talk about inverses? I know you guys are excited about talking about inverses, which is good because they're exciting. But do practice those. They do take a fair amount of practice to get good with the graphing, particularly to get fairly quick with the graphing. When you're doing something like a test, you really don't want a graph to take you very long because you can get bogged down, spend 15, 20 minutes trying to graph something and need that time somewhere else. So you want to get enough practice with graphing that you're able to throw out those things fairly quickly without getting kind of overwhelmed by it or without getting stuck in little pieces, because it can eat up a lot of time if you haven't practiced. So inverses. For functions in general, we think of functions that have or are inverses as being opposites of each other, being functions that undo each other. So for example, the function x plus 2, it has an inverse of x minus 2. The function f inverse undoes the function f. If we take a value, put it in for x, like say 8 plus 2 is 10, put that 10 in here, the 10 minus 2 gives us back our 8. That's what inverse functions are supposed to do, reverse the operations. Do notice it is not 1 over x plus 2. This is not the numerical reciprocal. This isn't 1 over f. That's technically the, if we wrote 5 to the -1, yeah, that's 1/5. But that's 1/5 because this is the multiplicative inverse. Exponents on numbers tell us how often to multiply. It's multiplicative inverse. Where else do we see a -1? If we have -3, well, that -3 is a -1 times 3. That negative makes it the additive inverse of +3. So that negative symbol really does say opposite. It says inverse, but there are different types of inverse. On a function, that -1 does not say I am the multiplicative inverse, I'm the reciprocal. It says I am the function inverse. I am the function which undoes the function I'm modifying. So it says undo f. It doesn't say take the reciprocal of f. So be very careful about that. Now, the trouble with inverses is not all functions have clean inverses. For example, if we look at something as supposedly straightforward as x squared and try to come up with, well, what's our inverse of x squared, we run into trouble. Now, what do you think of? I'll give you a minute here. What do you think of when you think of the inverse of x squared? We actually use it all the time. Make you guys talk to me today. Whether you like it or not. What do you think of as the inverse of x squared? Yeah, I got some square root of x. Got to be careful with that plus or minus. It is technically the square root, not the plus or minus square root. But that plus or minus actually does bring up the issue we're talking about, Felix, because the question of what is the inverse of x squared, the technical answer is there is no inverse to x squared. And I'll show you why. Even if we say it's the square root of x or plus or minus, this technically doesn't work because keeping in mind that functions are supposed to be, the rule about functions is one input gives us one and only one output. That's why the plus or minus can't be there. If that's the rule, then if we take a value and put it in here for x, let's say, 5, put that in for x and we'll get 25. Great. Take that 25, put it into the square root. What's the square root of 25? What's the square root of 25? Don't let me down here. 5. Yeah. So we got back our 5. Great. That's what inverse functions are supposed to do. But if we go over here and say -7, plug in the -7, -7 squared is 49. What's the square root of 49? What's the square root of 49? 7. Yeah. We didn't get back the -7. The inverse function didn't work. And it can't. It's not plus or minus 7, because remember, functions one input, one output. Plus or minus 7 is the solution to x squared equals 49, but we're not solving. It's one thing to be careful of. Like the square root of 9 is 3, period. It's not plus or minus 3 because this is a function. Functions have one input, one output. If we try to solve x squared equals 9, that gives us the plus or minus 3. And the reason it gives us plus or minus 3 is because we take the square root of both sides. And again, what's the square root of 9? It's 3, period. The issue is this square root of x squared isn't a correct inverse because it doesn't work. The square root of x squared is not equal to x, no matter how much we want it to be. The square root of x squared is the absolute value of x. That's why we got the +7 out instead of the -7 out. Fair? And then if we solve this for what x values is the absolute value of x equal to 3, well, that's true for x equals +3. and x equals -3. So that plus or minus actually comes not from the square root of 9. The plus or minus comes from this side, from that square root of x squared. Now, a lot of your training makes you not want to do that. A lot of your training makes you go, okay, if I've got that, and when I take that square root, I got to put that plus or minus here, convinces us that the square root of 16 is plus or minus 4. It's not. It's 4. This style also convinces us that the square root of x squared is x. It's not. If we take -7 squared square root, is that equal to -7? No, it's equal to +7. Again, all of this issue is because the square root is not a perfect inverse. The reason it's not a perfect inverse, or one of the ways we can see that it's not a perfect inverse, is because the x squared function is not 1-to-1. Just like we have a vertical line test to see if it's a function, a horizontal line test will tell us if it's a 1-to-1 function, if it can be inverted. The fact that at 25 we have two different values, 5 and -5, that it can come from, tells us if we try to reverse this thing, it's not going to work. Same thing at that 49. The fact that both -7 and +7 both yield a 49 means when we try to invert this and go from the 49, we're not going to have one and only one answer. So what do we do? What have we done for hundreds of years with this to make this work? We always say this is the inverse function for x greater than or equal to 0. We pretend that this side of the function doesn't exist. And we only allow our square root function to be defined where those x's were positive. That's why we can't take the square root of a negative number, because we got rid of all the negatives. We threw them out. We don't care. Similarly, if you graph the square root function, the graph only has that one curve to it. Well, it's trying to be a flipped x squared. If you take the x squared, and you guys know how to build inverse functions, you rotate the graph around that line y equals x. If we rotated that, our function wants to be this. But that can't be a function. It doesn't pass the vertical line test because the original function didn't pass the horizontal line test. So we have to say, for our inverse to be valid, we won't let x's be negative. Felix, you're asking, why can't we say there is one answer, but we can only find it with 50% accuracy? In either example, x was definitely 9, not -9, though we seem to lose that through the absolute value. Both example, the x was definitely 9. Yeah, the x was definitely not -9, but that the value that can be in that x to make the straight statement true can be both +3 or -3. So that's where the we don't know which one it is. And having one answer that's only has a probable output is a big kettle of fish we don't want to walk into for this. What we do instead is we restrict our inverse functions and make sure we know things like, hey, make sure we put that plus or minus on it to know that we've compensated for the fact that we restricted this function when we built the inverse. Now, why am I talking about all this when we're supposed to be talking about trig functions? Well, if we look at the sine function is so very, very not one-to-one. This thing doesn't pass the horizontal line test a lot. So if we tried to say something like, okay, let's take the sine of pi over 6, and we know the sine of pi over 6 is 1/2. So at pi over 6, it's 1/2. Then if we want to build an inverse function for this, sine inverse, that inverse function should be a function that takes in this 1/2 and gives us back one and only one answer. Well, the trouble is this sine function, assuming it doesn't know where we came from, if we had just this sine function all by, or sine inverse all by itself, then that inverse function has no way to tell us which one of all of these angles, it's supposed to give us, because all of those angles make the sine equal to 1/2. So similarly to our x squared square root example, we have to agree to a restriction on the sine inverse for what angles it will give us. We have to essentially pick which one of those infinitely many angles is the sine going to push out. Felix, you said restrict it to the first period. I like that idea. The first period goes from there to there, from 0 to pi over 2. So say, okay, it only is allowed to give us answers in the first period. Fine. Then the sine inverse of 1/2 will always give us the nice answer in the first period. Great. If we ask what is the sine inverse of the square root of 2 over 2, even though we know there are infinitely many angles that give us the square root of 2 over 2, the only one that's in that first quadrant is pi over 4. So we'll agree the sine inverse of root 2 over 2 only outputs pi over 4. I don't mind that at all. Does that seem reasonable so far? Felix's restriction? I do have one problem with your restriction, Felix. What if I have negative square root of 3 over 2? In that first quadrant, in the space between 0 and pi over 2, the sign value is never negative. And I want to be able to ask what is the sine inverse, what is the sine inverse of negative square root of 3 over 2? So your restriction, while I like it, it's too restrictive. It's too much. We need a little bit more room so we can have negative values as well. But we got to make sure we don't put in double countings or put in repeats of the positive values. So where else would you like this to be defined so we get both all the positives once, like you have them, and all the negatives once? Suggestions? You guys being shy, or have I lost you, or are you worried? First and third quadrant. We could absolutely do that if you wanted to. We could say we're going to go with that first quadrant to give us all the positives from 0 to 2 pi, and use the third quadrant from pi to 3 pi over 2 to get those negatives. we could do that. We could define it from, oops, I don't want that. Define it from 0 to pi over 2 and, or unioned with, from pi to 3 pi over 2. We could do that. That would totally work. But I don't want to do that. The reason I don't want to do that is because these are two separate regions. They're disjoint from each other, and that's inconvenient. I'd prefer to have one region that has all the positives and all the negatives. So I really like your idea of staying in quadrant 1. So is there a way we could stay in quadrant 1 and expand it to get the negatives without having to have a jump in between them? How about we go this way? That's technically the fourth quadrant. It's just the negative version of the fourth quadrant between negative pi over 2 and 0. So instead of doing this, which again, it would work, but how about we go from negative pi over 2 to pi over 2? That way we can be one chunk instead of two chunks. Now, you could argue that, yeah, it's two chunks, but I'd rather have them be positive than have some of them be negative. And there's certainly an argument to be made there. Unfortunately, over the last couple hundred years, the entire mathematical, physics, and scientific communities have agreed to use the restriction from negative pi over 2 to pi over 2. So even though it would work either way, we're going to follow that convention to make the restriction from negative pi over 2 to pi over 2. Similarly, by the way, you can define the square root of x to only work on negative numbers and not positive numbers. The implications are cool. It doesn't actually change anything. It just makes the mechanics weird or feel weird. So essentially, just like for the square root, we're only allowed to give the positive result, for sine inverse, we're only allowed to give a result that's between negative pi over 2 and pi over 2. So if we ask, hey, what is the sine inverse of negative, I'm going to stick with a standard result for right now, negative 1/2, well, we go to our unit circle, it's a terrible circle, sorry, and we look, where is sine negative 1/2? Well, the y value is negative 1/2 down here in quadrant 4. It's negative 1/2 down here in quadrant 3. It's positive 1/2 in quadrants 1 and 2, so they don't count. If we look at what angle this is, our unit circle tells us this is 11 pi over 6, right? Well, 11 pi over 6 isn't in this restriction, though. 11 pi over 6 is over here. Eleven pi over 6 is way over here. The sine inverse doesn't know that exists. The sine inverse only knows about this dark blue section. So it can't give us that 11 pi over 6. What's it going to give us instead that's coterminal to that and gives the same answer? I'll let you put that in the chat or say it out. Get you guys involved. What angle would be right there that would give us the same value as that 11 pi over 6? Well, it's on this side, so it would have to be negative. And it would have to be coterminal to that 11 pi over 6. So, yeah, Shay, the negative 1 pi over 6 is the sine inverse of negative 1/2. Now, if it wasn't one of our nice standard angles, we could still find, say, the sine inverse of, say, negative 0.873. This negative 0.873 is some ratio. We want the sine inverse function to tell us what was the angle that created that sine ratio. Because remember, the sine function by its nature, the sine function takes in an angle and gives out a ratio. So what does that mean the inverse function has to do? Its job is to take in the ratios and give us back the angles. So we have a sine ratio of negative 0.873. We want to know what angle that was. Well, it's not one of our standard angles, so ask your calculators. Grab your calculator, use your inverse sine. That's the second sine command, the sine with a negative 1 on it. And ask it what the inverse sine of negative 0.873 is and see what you get. I'm going to wait until I get at least 5 answers, maybe 6. So I want you guys to make sure you're going along with this. Quiet today. Yeah, I want 5 answers that don't include Shay and Felix. Just because you guys are awesome and you talk. So don't bother. That's your choice, Felix. So I'm seeing a negative 60 point. I'm just going to round that to 8. I got a negative 1.061. And Keegan, you asked a great question. Are we supposed to be in radian mode or degree mode? If this is an angle, it could be either one. That's frankly why we got 2 different answers here. It's nice that the 2 first answers that popped up was one of each. So this 60.8, I could criticize you a little bit, Garrett, for not saying 60.8 degrees. Yeah. Now saying negative 1.061, that's automatically radians because you didn't say anything, right? But this is technically, if you didn't say anything, it's technically in radians, so we do want to be careful. But either answer is perfectly reasonable. I'm going to go with the radian answer just to irritate anybody who hates radians, because you got to learn to like radians. So notice it gave us a negative angle and a negative angle in quadrant 4, because that's less than pi over 2. So it's less than, well, technically greater than negative pi over 2 would be negative 1.57. So it gave us an answer in quadrant 4 as the only answer it gave us, because that is the only answer sine inverse knows about. If you're in degree mode, it'll give you the one answer in degree mode. If you want to play around and check, these are the same angle, one in radians, one in degrees. So this is the first important thing to understand about are inverse functions, is that what they do, their job is to, instead of being given an angle and give us back a ratio, their job is to take in those ratios and give us back angles. So when we need to find angles, we will be using inverse functions to do it. That's their job. But because it's not a one-to-one function, because each angle or each ratio comes from so many different angles, for it to be a well-defined function, we have to restrict it to what is the one angle we're going to get back. For sine, that restriction is between, for angles in the interval from negative pi over 2 to pi over 2. Unfortunately, the other trig functions don't necessarily have the same restriction. That's the bad news. So for sine, yes, we restrict sine from negative pi over 2 to pi over 2 because we need that one instance of each value from positive to negative without repeat. So every possible ratio has to occur, but only once. That's for sine. For the inverse function, that is the only part of sine the inverse function knows exists. However, for cosine, we can't use that same interval. If we did, we wouldn't get what we want. Let's say we tried to do that. From negative pi over 2 to pi over 2, cosine looks like that. Not only is it not one-to-one, but it also doesn't give us any negatives. So that restriction's not going to work. What restriction are we going to use instead? Shay, 0 to pi? Yeah. If we go from 0 to pi, at 0, we start on top. Equilibrium at pi over 2. Minimum at pi. That restricts cosine to 1-to-1. So as far as the cosine inverse function is considered, angles only exist from 0 to pi. What about tangent? In some ways, tangent is the nice one. Because if we try to graph tangent, we automatically think about tangent as being a bunch of these big sweeps, right? Those sweeps naturally go from negative infinity to positive infinity. They go through all the possible ratios that tangent could give, and it only does it once. And we already know where those asymptotes are. So for the inverse functions, for sine, we only consider angles that are between negative pi over 2 and pi over 2. For cosine, we only consider angles that are between 0 and pi. And for tangent, it's almost, but not quite, the same as sine. For the tan inverse, we only consider angles from negative pi over 2 to pi over 2. But notice the parentheses, we don't include the pi over 2 or the negative pi over 2 because tangent isn't defined there. So slight difference in that restriction, but only slight. So, for example, if we want to know the tan inverse of, I don't know, let's say negative 4.3, what quadrant is that angle going to be in? Because remember, the inverse function outputs an angle. So this is an angle. What quadrant is that angle going to be in? Again, I'm going to wait for a couple of answers. You only got 4 choices. 1, 2, 3, or 4. Got 1 answer. Felix, you can answer this time if you want. Never be afraid to be wrong. Being wrong is the best thing you can do to learn anything. I love being wrong. It's the only way to learn how to be right so often. My mother hates when I say that. Everybody hates when I say it. But I often say the worst thing you can do with any of these problems is get them right, because you don't learn anything if you get them right. So bad shag, you didn't learn nothing. See, not being afraid to be wrong. It's very important. Now, in a lot of ways, 2 is not an unreasonable answer, because that tangent is negative, and we know tangent is negative in quadrant 2. So in a lot of ways, 2 is a very seemingly reasonable answer, except that quadrant 2 goes from pi over 2 to pi, from pi over 2 to pi. And the inverse function doesn't know, the inverse function for tangent doesn't know about angles in quadrant 2. It only knows about angles in the negative version of quadrant 4, between 0 and negative pi over 2. We think of quadrant 4 as being from 3 pi over 2 to 2 pi, and it is. But remember, all of the quadrants come up over and over and over and over again, right? So which copy of quadrant 4 are we in? We're in that negative first copy of quadrant 4. So it only knows about things in quadrant 1 and 4. So the angle that we're going to get from the inverse function has to be some angle down in quadrant 4. And if we use the calculator to find out what that angle is, we better get an angle in quadrant 4. Or everything I'm saying is wrong. Wouldn't that be scary? So when you ask your calculator in either radians or degrees, what is, let's do this in degrees just for, so we're all on the same page because we've got to go soon. But what is the tan inverse of negative 4.3 in degrees? Probably pretty high, like 60s or so, or no, maybe even 70s. I don't know. Negative 76, negative 76.9 degrees. So negative 76.9 degrees. Yeah, solidly in quadrant 4 and solidly in that negative version of quadrant 4, negative 76.9 degrees. Fair? Now, one of the things that's going to happen a lot is we're going to be trying to figure out like the direction something goes in. And the inverse function is only going to ever be able to give us this answer. But just like we have to deal with the plus or minus when we solve equations with x squareds and square roots, when we start using this to solve, we're not only going to have to live with this restriction, live with the fact that the inverse function will only give us this one answer, but we also have to learn to fix that answer to find the other possible angles. So we first have to we'll spend time tomorrow working with these functions by themselves and working with these restrictions. But later in chapter 7, when we start solving, we'll have to learn how to deal with these restrictions and be able to undo these restrictions. So look forward to that in chapter 7. Tomorrow, we'll talk more about the problems like, the sine of the cosine inverse of, some of those cool problems. Those are actually neat problems. As a preview, my clock has another minute on it, but yours might not. As a preview, if we ask what the sine inverse of the sine of, let's say, pi over 6 is, what do you think the sine inverse of the sine of pi over 6 should be? I know we have to go, so I'm going to consider that question rhetorical. But ideally, the sine inverse and the sine should undo each other, yielding just the pi over 6. That's the job of the inverse function. The problem is, if we ask what the sine inverse of the sine of, let's say, 7 pi over 6 is, well, the sine of 7 pi over 6, okay, is some ratio. You'd want to say that if you put that ratio back into the sine inverse, it would give us back our 7 pi over 6, but it can't. The sine inverse doesn't know about 7 pi over 6. It's only going to be able to give us an answer that yields the same result as 7 pi over 6, which is -1/2, by the way, but lives in the quadrant 4, the first negative part of quadrant 4, because that's our restriction. So it's not going to give us back the 7 pi over 6. It can't even give us the 11 pi over 6, because that's in the positive rotation way out here somewhere. It has to give us that negative pi over 6 back. Pi over 6. Negative. And that is exactly the same issue from where we started today with what's the square root of -5 squared. We want the square and the square root to just undo each other and say, hey, that answer is -5, but it's not. The answer to this is +5. It's the value that gives you the same answer as -5 squared, still gives you 25, but within the restriction that the inverse knows about. Fair? Takes a little bit of wrapping your head around. So we'll play with a bunch of these tomorrow. We'll kind of switch the functions up and have them interact with each other a whole bunch. And then we'll be done and we're ready for your test on Friday. Oh, somebody did send me a message asking about taking the test early because they had a big thing on Friday, or said they could take it Thursday or Sunday. I made a note, but I don't remember who that was. If it was any of you, send me a note. I think I have it written down, but it just reminded me and I got worried. Anyway, we'll make it worked out. We'll work it out. Oh no, I told them to. No, it's fine. I got it worked out. Never mind. I panicked for a second. Sorry. I should have stopped recording before I said that. Now it's all embarrassing and in the world.